Are we waiting for someone else, or we can start?
Just give me a moment to post links in the in Discord.
Sure.
Probably no one is going to join, but anyway.
I think we can start, and like people will join.
Okay. Yes. Sorry, I had to just set something up. Yeah, let's start. So welcome everyone to the first seminar for the year. And now Ivan Klimuk will present to us a technique for time series analysis with, what was it called? With attention or something like that?
Yeah.
Okay.
Give me just a second. I'm trying to share my screen because I have these new security settings with the new macOS. Can everyone see my screen?
Yes.
Yeah, I can see.
Like, I'll be talking about transformer neural networks, and like I really couldn't resist to put some actual transformers into this presentation to make it a bit more funny. So yeah, welcome everyone, and I will be talking about this new neural networks architecture that tends to be really good at sequences analysis, particularly in text analysis and time series classification and forecasting. So the agenda will be the following. I'll be quickly going through the previous state-of-the-art architectures, so the best performing neural networks that have been used before the transformers were invented. I'll be also talking about the sequence-to-sequence model, which is built on top of recurrent neural networks. Then we'll be talking about attention, the transformers themselves, the internal mechanisms and why it's so good, and how you can apply them for time series analysis, and what are the challenges in applying them particularly to time series. Yeah, so as you may know, like the very basic neural networks, they look more or less like this. So you have some data at the input. You have a bunch of units, like standalone units. They are called neurons, and they apply some to the basically to the numbers in your input vector. They do this multiple times, layer per layer. then you can calculate the error on the end and backpropagate the error until like the neural network gets real good and you can stop the training. In recurrent neural networks, the main idea is basically the same, but what they also have in comparison to regular neural networks is every neuron. So in a regular network, you connect every neuron on one layer to every neuron on the next layer. So the data from, let's say, this unit, it goes to all of the units on the next layer. And in a recurrent neural network, as the name might tell you, all the data flows to the next layer. Data from every neuron flows to the same layer, basically to all of the neurons on the same layer, and even from this neuron to itself. This is used for keeping information sample. So you pass some data to this neural network. It analyzes it, does all the math. The calculations, the result of the calculations, it flows to the next layer, but it's also being kept for the next iteration. So once the next data sample comes in, these guys, they also take into account what has been the result of the previous calculation. And this is naturally done to analyze any kind of sequences. And actually, like this is again on how they work. To be honest, I actually always found them pretty confusing, but this is probably the best way to interpret it. So this is again one neuron or one layer of recurrent neurons, and they are cycled. So each time you pass something into them, they calculate this result, and also they pass the same result to themselves for the next time. So this one is enrolled in time. So here you have the time 0, time 1, and etc., etc. And they're actually really good at processing sequences because all of the text analysis frameworks, all of the text analysis models that have been used by these big companies like Google, Facebook, and so on, they've been completely based on this. And actually, these models are not really new. They have been known since the 70s, I guess, and they had quite a lot of problems. For example, if you backpropagate the error, as I mentioned here, like you need to do this layer by layer, will propagate the error over time. So, for example, from this hidden state, because of it stands for hidden state of this cell. So if you propagate the error from this one back to this one, then you calculate the error here, and using this this hidden state, you propagate it back here, and so on. You might face issues with longer sequences because the gradient will be getting smaller and smaller, and point of time it will be just vanishing. So you can't really build huge models, multiple layers, and with many neurons that can analyze long sequences, because it will just lose information while trying to backpropagate it through the model. And that's sophisticated stuff like long short-term memory cells, extensions of recurrent neural networks, but they also have an additional channel that keeps the information about what data, like what information actually to keep in this time step, and which to forget. So this is called the memory gate, or the like the memory channel or forget channel. And these internal operations, they are just invented to properly do this. So you pass the data, you take the previous hidden state, you take the information from the memory channel. So in this one, you actually calculate what to forget. Here you calculate what to take from the new data, and here you apply the nonlinearity itself. So this one comes from the actual recurrent And these guys, they have been working really well. There have been some extensions like the GRU. This is basically an LSTM cell, but without the additional memory channel. So everything happens just with the hidden states. And yeah, really well, especially for text, and basically everything that is related with sequence analysis with neural networks, it comes from text analysis, because the unfortunately, or maybe fortunately, I don't know, because these natural language processing problems in general, they the development of new models or the research in this area, because I think the biggest sequential data we have is basically text. And that's why people like the newest and best working stuff usually comes from natural language processing. And here it is the same. So for several years, people have been using sequence-to-sequence frameworks for machine translation. And this basically works as follows. So again, here, this whole thing is enrolled in time. Not actually multiple recurrent neurons or LSTM neurons, but rather like they're involved in time. So keep that in mind. And it works as follows. You start passing the tokens here in this sentence one by one. You can either pass them as just index tokens or use some embeddings to represent each word as a vector, which is much better, because like the more information you are able to pass through a network, the better it is. You pass them one by one, and it accumulates the hidden state. So basically, when you pass she, like this whole layer, it gives you a hidden state. Then you pass the next word, the hidden state updates, and so on, until we reach the end of the sentence. And then we have a vector, which is basically the hidden state of the very last state of the LSTM layer after the very last word. And this vector is also called the context vector. It is being passed to a second model, or a second part of the same model, which is called the decoder vector, and it's being trained to the sequence one by one, but in a very different case. So in this case, it's a different language, and this tends to work really well. In researching like how this can be improved. So this is and I think this one, some of you might have seen it as well. This is an animation, how it actually works. And here you can already see the word attention mentioned. The best improvement that people managed to invent for this, they okay, we're this context vector, this hidden state vector, by passing word by word, or like some point of time, one after another. And every time you have a fixed length vector at the output. And in the end, once you pass all your desired sequence through the input, you have only a fixed length vector. So basically, all of this information that you have, you squeeze it into one vector. And why would you do so if you can information from the whole input itself as well? And that's the main idea.
Sorry, can you go back to the previous slide? So just to make sure, for me at least, that I've understood what's happening here. So you have this recurrent neural network, and it has like inputs, and you pass to the inputs this sequence of words. And so this network has some kind of state. So when you pass, is
the hidden state is basically the output of
okay.
the.
I see.
Let's say
Okay.
we have only. And
okay.
its output is a fixed length vector. You pass a new word, it takes this word and the previous state, the previous output.
Okay.
Being done one after another until we reach the final word or the maximal length, let's say. And after that, you say, okay, I'm finished with my input sequence. It looks like this. Let's give this output to a decoder and do the same vice versa. Let's now decode one by one.
Okay. Okay. So at the end, you have this output. Is this vector just the sequence of outputs from each input, or is it just the final output?
It's just the final hidden state. It's the final hidden state once we finished putting input. So once we finished feeding the one by one, we look at the final output, and that's it. And that's actually the issue I'm talking about. So
okay,
you have many hidden states, but you use only the last one to decode the stuff.
Okay, so in this case, basically the output for this particular neural network is 5 numbers, right? So for the first for the first word. Okay, I'm sorry, I can't hear very well.
Yeah. For the very first word, usually when you start feeding something from a sequence, for the very first word, this hidden state is usually 0. So we feed the very first word to the recurrent unit. Back.
Okay.
Recurrent unit. Like X is a word. Like a word represented by a vector. And if it's the first word, then we just ignore this input from the previous state because there is no previous state.
Yeah.
Uses some output.
Yeah. My questions.
And put it again.
My question is on this picture you have xt and you have ht. So xt is like the words that we input. Ht is the output. So here, if you look at the example, so here ht should be a vector of 5 numbers. If we apply this to this example, am I correct, or is it just one number or something?
No, it's a vector of 5 numbers, but 5 is just a matter of design. So it's actually like usually more. So that's just for the sake of simplicity.
And then you input those numbers one by one into the decoder?
No. You put the whole vector decoder, and it starts decoding. When it decodes this word, it also takes into account the output of this decoder and the like it takes into account this input and the output as well. So the issue here is that let's say if it makes a mistake here, then this word is going to be wrong as well, probably. Can look at is the previous word, which is already maybe incorrect, and only this hidden state.
Okay, so in this case, your decoder, you get input like a vector of several numbers, and then it outputs 2 things. One thing that it inputs is a word, and the other thing that it outputs is a new vector of 5 numbers, and this vector is passed to the next run. Is this how it works?
Yes, I think yes.
Okay.
Or maybe let me quickly think. So it takes this vector of 5 numbers in this case. It managed to produce and produces a word out of it. So it's trained specifically for this.
Okay.
Yeah. And as I mentioned, the issue here is that it takes the hidden state only from the very, very last word. So basically you have a lot of hidden states here. So a lot of information passes through the network words one by one. but you take into account only the last hidden state, which is an issue. By looking at all of the hidden states, so here, like the decoder is actually on top. That's just the original paper. Instead of taking the very last output, you also into the decoder, you not only feed the very last output, the outputs produced and put them into the decoder. So just as you would do in a regular feed-forward neural network, inputs, apply some weights to each of them and put them in the next into the next layer. You do the same here. So instead of looking at just one vector, you look at all of the hidden states of the previous one with some weights. And the cool thing is that you can actually train this weight. So you can make a model learn how to properly look at them. It's like, let's say, x1, x2, x3, xn are the words or the time vectors. So are vectors that represent one word. You feed them into the encoder, it produces some output. And this is the thing, this is the case for each of them. And you, instead of looking at only the very last output, you look at all of them with certain weights. And these weights, they can be trained. In this case, they also, they feed the sequence in the straight order and also in the vice versa order. So that's just like an engineering trick. So you like basically this works only for text, because in text you can look at the sentence from left to right and also from right to left, but that's not really important. The important part is that instead of keeping in memory only the last one, you can look at all of them. And it's called attention because you train the network, the model, to pay attention to specific things in the past to actually produce something or learn some information for the future. Yeah, and this is how it's done mathematically. As I mentioned, these weights can be trained, and actually, so this is the context vector that you pass here. So this upper part is the decoder. The decoder takes the, let's say we are in the middle of the decoding process. We take the previous hidden state, the previous word we produced, and also we take the context vector. And this is being done by calculating a weighted sum of the hidden states of the input of the words we've been inputting into the network. And the weights are calculated as a softmax function of certain scores. So for each of these hidden states, you assign a score. This score is relative to the decoder's hidden state, and is calculated as a hyperbolic tangent. But that doesn't really matter because there are various types of attentions. So the main idea here is that, as I mentioned already before, we don't lose all of these hidden states. Like we don't just go one by one, but we feed all of them with certain weights into the decoder. So the part of the model that decides what to do with the information it gathered from the past, it doesn't only look at the very last point of time or at the very last word and what happened with it, but it looks at all of them with certain weights, and it learns these weights. That's why it's called attention, because it pays attention to different points of time in the past differently. This is just a table with, as I mentioned, there are like a lot of types of attention. This is basically a matter of engineering and like math tricks to apply. One of the most important ones that I'll be talking soon is this one, the scale.product. But this doesn't matter, it's just like, so you can see that there are a lot of them. And here are some visual examples. So actually attention is also applied in computer vision. It's applied a little bit differently, but the main idea is the same. So along with the main model that trains to just classify an image, it also learns to capture particular parts of the image in order to be better at classification. This is for the text. As I mentioned, you learn not only to look at the very last word. Let's say if we want to translate this sentence into a different language, we won't only look into the output of the neural network after it sees apple, but we look at all of the outputs that the network produces once it analyzes all of these words. And then we can capture the semantics, the relations between the parts of the sequence differently. And if we are talking about text in the end, this attention thing, it can be interpreted as a nonlinear weird way of correlation. So it's not actually correlation, but it's a matter of it's a way to measure the way the weights of how a certain word in the input affects the output. So for example, these words, they are pretty straightforward, they're connected pretty straightforward. But for example, for these several words, when you translate this word, you not only generate this one, but vice versa. If you translate this word, so you take this one, you also look at other words. So this is the main concept. You use everything from the past and try to look at not only the last state, but at several of them. And this idea was so exciting that Google Brain came in and said let's get rid of the LSTMs and recurrent stuff and just use attention only and introduce it as a new architecture. So they published in 2017, they published this paper, Attention is All We Need, where they basically introduced a new architecture that uses only the attention mechanism together with regular feed-forward neural networks without any recurrent logic, recurrent units in general. And here's how it works. So this is the architecture itself. I'll go through all of the blocks. It might look complicated. It maybe is complicated, but it's I really like the idea, and it makes sense to me, I think. So yeah, on a high level, you have the same as the sequence-to-sequence model. You have an encoder and a decoder that processes basically an input sequence and an output sequence. And this is obviously done for first of all for machine translation. And if you want to do to perform other tasks, like let's say you need to only classify the input sequence and that's it, you can get rid of these complicated decoders and just use a simple feed forward, like a bunch of fully connected layers on the output, or you can use several encoders, several decoders, and in the end just output a single number that will be the probability of whatever you like. So you can play around with the with the output of the network to fit your problem. Yeah. So this network works best with vectors. That's why when you're working with text, you need to embed them, and that's what they do. So they usually use embeddings. So before putting words into the model, they use embeddings, which is something like word2vec or a glove or any other vector representation of words. And they also apply positional encoding. This is something I won't focus on today, but because it's specifically important for texts, and in time series analysis, it's actually covered by a different mechanism. I'll be talking about it later. But yeah, positional encoding is just some weird method that they add to the embedding itself to tell the network more about the position of the word in the sentence. But this is something very specific for text, and actually, like, people argue if this is really something needed here, because this positional encoding, it has a lot of empirical constants, and it's really not obvious. It's basically some cosine transformation of the input embedding itself. Yeah. So this is how one of the encoder units look like. And like on the next several slides, I'll be going through examples with two vectors. So let's say we are analyzing a sequence of two vectors that can be, for example, two words or 2 points of time. But for the beginning, we'll be talking about text, because we need to care about less stuff when we are talking about text. Because when you're analyzing text, you basically don't need to care about the future data points. Like, you don't need to hide them. So yeah, as I mentioned, you like in the encoder units in these transformer encoders, they put them like we first get vectors from words, which is done in any convenient way, like whatever we like, and then we put them into the network. It goes to a self-attention layer, and also the same information bypasses the self-attention layer and goes directly to the next layer. This is called residual connections, which is a pretty old and well-known technique, and this is done for like keeping as much information as possible, also after applying some nonlinear stuff. So yeah, the output of the self-attention layer together with the input information itself is then added and normalized in a specific way. It also doesn't matter how, like, this is something that can be easily changed. And after they are added and normalized, they are fed into a regular feed-forward neural network, again with the residual connection, again with the addition and normalization in the end. And this is how one encoder works in general. And the very, very important part here, and the most sophisticated part here, is the self-attention module, which looks which looks internally like this. So this is a visualization of how the attention can be interpreted, and why it's actually called self-attention, because as I mentioned previously, when we've been analyzing sequences to sequences, we've been transforming one kind of sequences, let's say words in one language, to a sequence in a different language. And we've been using attention. So we've been paying attention to stuff in the previous, like in the other language, to generate stuff in a new language. And self-attention is actually called self, because here you learn to pay attention to things inside of the input sequence itself. So you don't have a second sequence that you're generating or analyzing. You just learn to pay attention to different parts of the input sequence and learn how important they are for for other parts of the same sequence. So here, it's visualized the same bunch of word tokens, actually words, but word tokens. And here we can see a visualization of how important the words in this sentence affect this particular token. So when we have a sentence that is like, the animal didn't cross the street because it was too tired, then when we look at it, the model, like when the model looks at it, it understands that it is mostly related to the animal, and like it thing. So that's it. And these words like because or they're not really important. And this is the high level of the self-attention thing.
Actually, this example is kind of funny because it can refer both to the animal and to the street. So if you change and the word tired, it's not relevant. But if you change the sentence to the animal didn't cross the street because it was too white, then all of a sudden it will refer to the street and not to the animal.
Yeah, that's the thing, and that's a matter of training this whole thing on a lot of different texts. So they used to train these kind of models on like Wikipedia articles, books, and so on. So like really on millions of examples like this. And also what I wanted to mention is that one attention block that produces these outputs, but as it's usually done in neural networks, once they implemented a self-attention block, they said like, hey, let's implement. Usually a self-attention block is used multiple times with randomly initialized weights. So we can, like for the very same example with this animal, there might be in the network, there might be another self-attention block that will be completely different. So it won't focus on the animal, but it will be focusing on it and was, because like it will be, first of all, it will be focusing on itself, which is kind of obvious and not the case here. And it was and it tired. So for example, like it's the logic here is the same as in a regular neural network. So different neurons learn to capture different parts of the information, and here it's the same. So the different attention blocks capture different learn to pay attention to different things for the same word. But mostly like experiments show that like it usually makes sense. So people have been studying this and trying to interpret them, which is actually one of the biggest advantages of also of self-attention attention mechanisms in comparison to recurrent neural network, that you can actually start looking at these weights, interpreting them, which is barely impossible with the recurrent neural networks, because there you have these hidden states that really they don't mean anything understandable. Here you can at least make these visualizations and see like it's paying the most attention to. Right. So like looking quickly through this model, through this module, the self-attention module, one block of self-attention works like this. So you have the input sequence, which is a sequence of vectors. Here, like x1 represents is a vector representation of the word thinking, and x2 of the word machines. I don't know why, like they just had these words for the sake of simplicity, only two words, and then you calculate like this is the most confusing part, but that's the self-attention block. It operates with queries, keys, and values, which is nothing but an abstraction. Compute three entities are also represented by vectors of numbers that are human understandable, but just a bunch of numbers that serve for different purposes. So they're calculated by multiplying the input on the weight matrix. You multiply the embedding vector on this weight matrix, you get the queries. You get the query Q1. If you multiply this vector on the next matrix, you get the key. Like again, the whole idea is that these matrices, they are trainable. So these weights, they adjust during training the most to be more meaningful for the model, not only random. And once you have these queries, keys, and values, you actually calculate the, which is done like this. So you first calculate the queries, then the keys, then the values, and then you take the dot scaled, the scaled dot product that I mentioned before, which is basically like you multiply normalize it by the size of the three entities, and then multiply it by the values, and you get called self-attention matrix. So each of the rows of these matrices represents the self-attention product, the self-attention result of each of the data samples. But all of this is done in parallel. So you can feed the whole sequence, the sequence of vectors, and it's being calculated simultaneously. And as I mentioned before, this is done multiple times because why not? Like, you have they invented one self-attention module, and then they said, like, let's take a lot of them and initialize them randomly, and they will learn different stuff. And it actually tends to be a viable idea. So they do this many times. Have multiple self-attention blocks. They call them heads. That's why it's called MultiHead SelfAttention. Each of these self-attention heads produces a self-attention matrix Z. Then all of these matrices are concatenated, multiplied by another huge matrix of vectors, and it produces a final matrix of weights that represent the overall self-attention for the whole input sequence. To the architecture itself, that's what's happening. So you put the input embedding into the network. It's being embedded in any way that is more convenient for you. If we're talking about time series, then we actually don't need this input embedding, because in time series, like, we already talk about vectors of numbers, which each of the vectors should represent a particular point of time. Then for text,
can I ask something?
Yes. Sure.
From the previous thing that you were explaining, it kind of seemed to me that yeah, each of those matrices, each of those self-attention like things, you said that they can be trained for something. Yeah. And then they discover different aspects of the input, basically, different relationships, something like that.
Yeah, different relationships are discovered by different heads. So
yeah.
like,
so
in the convolutional network.
Yeah. So is it correct to say that we can kind of get let's say a theory, like a reason why an output is what it is, because I think a lot of machine learning algorithms act as a black box. So you put some input, you get some output, but you have no idea why this output was chosen. But does this help here to actually understand why the output was chosen, and what are the actual theory which the network discovered behind the?
Yes.
Okay.
That's exactly the point. It's also so I put some reference links in the end, so you can look at the articles later on. They have like really a lot of examples with sentences of text, and they show you like which words this model has been paying attention to while doing some stuff, while classifying it or while translating it, and so on. So this is exactly the point behind attention, and that's why it's called attention. So you can interpret these weights just straightforward, and this brings some clarity to the models. Yeah.
Thank you.
Coming back to the architecture, again, we put the input in, the multi-head attention, as I mentioned, which is basically a bunch of attentions that is being trained. Then you have some addition and normalization, a regular feed-forward neural network, and this is done multiple times. So in the original paper, they had 6 blocks like this, one after another, and then they feed the whole input into a decoder, which is exactly the same. So the architecture is exactly the same, apart from this small part. The multi-head attention is actually masked. And here it's done because when you decode stuff, you basically predict a new word. About text, you basically predict a new word in a new language, let's say. And once you want to predict the next word, you don't really want to look at the words that will be coming training. So like right now we are talking about training the model, and when you train the model, you already know the answer in the new language, right? But once you feed the the correct answer one by one, you don't really want to know the further words because this is cheating. It's like the same as looking at timestamps in the future. So you mask them, and this masking is done by assigning infinite scores future words, which results in zero weights in the softmax coefficients. So it completely ignores the values because otherwise this model would be overfitting to the future. Yeah, and here we're coming to the transformers for which, as I mentioned, they have several difficulties, but people really started using them for time series as well. Especially there are several works related to some medical time series, and I think also some guys have been using them to predict different things like traffic, humidity, and stuff like that in San Francisco, I guess. So they've been applying this successfully, and I think outperforming the previous best results on various data sets. And yeah, for time series, the things are a little bit different. Like as I mentioned, you don't really need to do any embeddings because you already deal with vectors of numbers, which basically case can be a set of metrics. Like we can take 10 metrics and they will describe one particular point of time. But as I mentioned, you can't pay attention to future points, not only in the decoder part, but we also need to implement this masked attention in the encoder part. So you can't feed the sequence one by one. I mean, you can't really feed the whole sequence and train the self-attention heads without masking the future points, because otherwise it will be meaningless, because you will, in one sequence of data points, in one sequence of vectors, you will train the model to look at the future ones as well, which is not just doesn't make sense. And I mean, for the further usage of the model. One more important thing is that you can't really use the proposed layer normalization, because again, you can't normalize across different points in the you either have to skip the normalization or use like instance normalization, where you normalize values inside the vector only. Like also these guys that I mentioned that have been predicting humidity and all of that stuff, they have been using some additional engineering tricks like convolutions to better capture seasonality. Like I'll show it in a few minutes. So that's what I'm talking about regarding the masked input. So we not only need to mask the output, and generally speaking, that's what I mentioned. So about, like, let's say predicting something based on a sequence of vectors that are representing date particular points of time. Let's say we take 5 metrics and we analyze them starting from now and back in the future. Like the input for our neural network, and once we feed them into the encoder, we actually have to, like once we calculate the attention for this particular point of time, really look at the time. So we have to mask them, and that's the case for all the other ones as well. And what I also wanted to say is that you don't really need the decoder unless you like want to analyze a sequence in the past and generate a sequence in the future. In this case, like, but this is multivariate metrics prediction. I don't know if it's like, I think it's much simpler to start with something like classifying whether like the simplest thing, like classifying whether the market will grow or not, or stay the same, and so on. So the simplest scenario, you don't really need this whole decoder. Like you maybe really only need the output itself. But again, as I said, you need to mask the input once you feed it, because we are dealing not with text but with time series. This is what I mentioned about the specific tricks. So before feeding the sequence into the attention block and calculating these queries, keys and values, you also go through it with the convolution, which is a well-known operation. And this helps to, like these guys claim that it helps to capture similar data. So instead of saying like, hey, these 2 points are similar, which are like they are kind of similar because they are on the same level, but this pattern and these, they don't really look the same. But instead, these two, they really do. So they in their paper, they show that applying convolutions to the sequences really helps to improve like the performance of the model itself, and helps to recognize seasonal patterns in it. That was basically it. So transformers, yeah, I think I didn't mention why they're called. So basically, they're called transform the data, they encode it in some representation, and then they decode it, and that's why they are called transformers. I don't know, to be honest, why the sequence-to-sequence model wasn't called transformer, but that's what they used to call it. So they are really, really good at processing sequences, and they're super fresh, and they have been implemented only recently, but they're already being used like Yandex and all the other big search engines. They're being used for analyzing texts, and they actually outperformed all of the recurrent neural networks and all of their varieties on the biggest NLP problems that we have nowadays. And as Sanko mentioned, and which is really great, is that these attention mechanism and these attention weights, they can be implemented, or they can be interpreted and explained much better in comparison to the hidden states of RNN-based models. But these models, the transformers, they have also some disadvantages. For example, they are really heavy and memory consuming. I think they are like comparable to the biggest. So you really need quite some GPUs to train them, and you also need a powerful machine to just run them. But I think they also are building like they are working on making these models lighter. I hope so. And one of the disadvantages more is that it's not that easy to quickly implement and test it, because as I said, so first of all, this whole thing, this whole transformer architectures, they are basically really new, and they are not implemented in any of the frameworks. And even if they would implement them, I think it still wouldn't be that easy, because the attention itself, it's as I already showed you, you can use like a whole bunch of different attention mechanisms. So you can't really implement a single block that's called attention and just implement it from like, let's say, PyTorch and use it straightforward. So you need to really implement this matrices operations one by one. So this also takes time. And I think Tim was trying to do this in the summer, but yeah, like he had different difficulties. Yeah, but again, it's not that easy to just quickly check it. You need to spend time to implement it, and that's one of the issues right now. And one more thing is that yeah, like they have a lot of problems, but also it's really cool that a lot of research is currently going on, because I feel like it's the same with as it was with computer vision, when in like 2012 basically everyone recalled convolutional neural networks and started building them because of one and in 2014 until 2016, I think, so like for 2 or 3 years, people have been inventing really crazy and really useful stuff on top of convolutional neural networks. And here, I think it's more or less the same. So this thing was invented like 2 years ago. It has been implemented by the very industry leaders, but nowadays it's getting more and more adoption. And I think a lot of applications and papers will be published like basically this year and the next year for sure. And I hope they will pay attention to analyzing time series as well. That's more or less it. I also left some learning sources that I've been basically using and looking into. There's also a great GitHub repo I found with different stock prediction models, and the guy there implemented these attention is all you need, but I think he didn't kind of didn't finish it, because I didn't really see in this particular case, I didn't really see some analysis of the results, but he started implementing it at least. And this is these are the original papers. This one is about the attention itself by Google, I mentioned, and this is the original article about BERT, which is the current state of the art, the most sophisticated language model that Google has developed on top of transformers, and which they use in their search basically right now. So that's it. Thank you for your attention, and I'll be happy to answer questions.
Yeah, thank you very much. That was interesting. Does anyone have any questions?
So there are no currently like any reference implementations of that?
No. So very high level libraries implemented by the community, but they literally implement the models mentioned in the papers. So you basically either import the whole model and that's it, and you have to work only with this model, or you have to implement it in the on the matrices operations level. So there's not really intermediate state right now. So they didn't really implement this, let's say, self-attention modules. They implement this query keys and values modules and stuff like that. So you can't, you're not that flexible. So you can either use developed, implemented models by the community, or implement it yourself. But again, as I said, this is extremely new. I hope maybe they will do something, especially Google. I think like they just released TensorFlow 2.0, and maybe they will add later on.
Okay, so could you please go back to slide number 16? Yeah, this one.
Mm-hmm.
So if you want to solve a regression task, can we use it like using the outputs from the first, from the encoder part? So basically, if we try to solve the the regression task, could we use the weights that are outputted by the input layer for this, like the actual things?
Mm-hmm. Do you mean, like, by regression, do you mean predicting one continuous
So
variable?
you said
Or
BERT is the newest one. How is that different from these general transformers? Do you know?
BERT? Hello?
Yeah, I can hear you.
Cool. Why? Like, Jan, can you please?
Yeah. Sorry, my
Yeah.
my mic was off, so I couldn't hear. Sorry.
I thought I had a like. Okay, so back to Alex's question. Alex, are you asking about regression in a normal sense, like predicting one particular continuous number, right?
Yes, but I'm also interested, like if it's possible to predict inputs like vectors.
Yes. So as I mentioned, you basically can solve it as a task. So basically, you can take a whole bunch of metrics, like let's say 10 metrics, a whole sequence of these vectors containing the metrics, and we try to predict vectors. But I think in case of embeddings, but predicting this will be like really complicated, and like when you generate the probabilities. So again, if you're dealing with the you basically predict the probabilities of the next word. So you're working with the fixed vocabulary, and if you're working with time series, basically the next value for any of the metrics in the vector can be anything. So you somehow need to either quickly. I think it's even not that straightforward. You need to somehow split these values into discrete buckets. Otherwise, I think so. Basically, running a regression for a whole vector is possible, I think, but maybe you can run. Yeah, no, I think it's possible, but it will be quite hard to run a regression for like 10 metrics at once. But you just need to basically, I think, remove the softmax layer here, and probably need the output embedding, because as I said, we are not dealing with the translation, with the text translation task, so you don't really need this part. You just have several encoders, maybe several decoders, and then basically they will be doing, I think, the same. So you just need several blocks like this, and then you feed the whole output to the linear layers. And if you're run a regular regression, you just remove the softmax because you don't need probabilities, and your network will be giving you a certain number. And if you like to predict like a whole vector of numbers, that's just a matter of putting multiple neurons on the output here. I think it might be the case.
Okay, thanks.
Yeah, Jan, what you've been asking about BERT? What's the difference?
Yeah. Sorry. Yeah. Exactly. So, is there any changes
BERT,
over the
I
normal
think
transformers?
I think so. So the regular transformer with attention is all you need is first of all implemented for translation tasks, and BERT is To be honest, I don't really remember the exact difference, but BERT is so it states for encoding representations from transformers. So the BERT is that it learns to represent words efficiently. So it's like a much better version of Word2Vec. And as far as I know, like the search engines, they use, so the text you type in, once you search something in Google, they, with the use of transformers, with the use of BERT, they
I think you're breaking up.
ranking your answers. Can you hear me? What was the last thing you heard?
So you told that is used like a super good version of embedded.
Yeah, so it's a much better version of embeddings, and they like nowadays when you type something in Google, embed the whole thing you said, the whole thing you typed in, they embed it into a multivariate vector and use it for ranking the search results. The other features that they can get from you, like geoposition and stuff like that. But they claim that this really boosted their search a lot. So these BERT embeddings, they are much better than the Word2Vec or GLAF.
Okay. Any other questions?
Yeah, I will share this.
Maybe only from product side. If you, Ivan, or other people from dev side, could you imagine
Maxim, you're breaking up also.
Yeah, could you please repeat the question?
is my connection better? Should be better now.
No.
Yeah, is any from dev side or data science can say what could be usage in the scope what we are doing at Santiment, identifying anomalies or saying this is important because of, and then saying because of what? What could be the usage?
Yeah,
well,
so basically you can use it for, we could use it for time series analysis, but my main concerns are that these things, they really work good with the very frequent data. So it really needs the granularity of the data has to be like 10 minutes or at least 1 hour. So you really need a lot of data points, and then we might make sense of it. And yes, we can use it, for example, for anomaly detection the same way we do, or for like proposing some signals. For example, we let the model predict some value in the future, and if it passes certain thresholds, we can fire a signal, and so on. The thing is that we actually could try to train language model on the text data we have, but again, we will get the pretty, like if we, let's say, use BERT for this, we will get a really good vector representation. But the question is like, what to do with this? We could use this for classification of the documents, but yeah, this is an open question. Like, by the way, right now I'm thinking that if we, let's say, feed somehow all the messages that contain the mention of a certain project, let's say Bitcoin, we could learn to, like we could look at what exactly attention in the messages themselves. Like this is something I need to think about. But yeah, so in general, this can be applied for time series analysis, like really sophisticated time series analysis, and to any kind of text analysis. to a really good.
And the interesting thing, if it works for time series analysis, to me at least, is that we can discover relationships like theories. So we can discover more complicated relationships than just correlation in time series. And then we can, so if you see it, then you can maybe even explain it using words. So you can say, okay, this metric influences this other metric, or this number of metrics influence those other metrics in the future in some way. Maybe something like this should be possible.
Mm-hmm. Probably, yes.
Would it be possible, I hope it's possible to hear me now. I'm using how it says as an attention, so please forgive me if I'm misusing the word. What was an attention of communication in the last 48 hours? And we say there is a bunch of text messages, and we say, okay, now.
I think my
Hello?
up, right?
You broke up again.
Now? Yeah, it's broken up.
No,
okay.
You use the chance. If it's an advanced version of word cloud, like an attention or topic recognition, would it work on our amount of data?
Yeah, question. But I think, again, so in order to be able to catch the most important things from the, let's say, last 24 hours, we need to tackle this problem as a summarization problem. So this is a problem where you have a lot of text documents, and you need the model to generate a short but very meaningful description of what's going on there. For example, you have a book and you have an abstract or a short summary of the book. Train a model to do this. This is possible, but for this we need, so let's say for every day, we either can go for models that are trained on general data, which I suppose will be not that accurate. So we can again train the models on books or something like this, like books and their descriptions, or news articles and their shorter descriptions, and try to apply it to data, at least to like only Reddit data. But if we want to make it really crypto specific, we need somehow to label it. And by labeling here, I mean we need to, like, for each day, we need to go to this day and say, like, for this 1,000 text messages, the short summary of them is this and this and this. Pairs, like a lot of examples like this, we can definitely apply this model, and yeah, we can basically use it for this, I think.
That would be interesting, yeah. The question is only, well, first question, if my connection is good. But assuming the answer is yes, the next good question is it enough? What is the minimum amount of messages we will need to get any reasonable result? 50, 100,000? So that a summary can be built, or like a set of summaries.
That's a good question. Again, it depends on how the model behaves in general, because one way to do this, and that's actually one more important thing I didn't mention about the language models, is
Ivan, you broke up.
I saw my Wi-Fi dropped for a second. So yeah, I stopped at coming back for a minute to the technical side. BERT is really, like the language model, is really good because it also, I think they claim that BERT supports transfer learning. So something you usually do in computer vision is when you train your model on general data, in our case, not crypto related, but just general text data, like as I mentioned, Wikipedia, books, and news articles in general. And then you can add 100 examples of what you need in our case, crypto specific texts like Reddit posts and Twitter tweets and stuff like that. Should fine tune or train specifically to your task. But again, this is something I don't know if it works or not, because people post these papers like every now and then, and I don't know, some of them are really useful, but like another implementation of BERT, we need to look into this. But in general, if like in the best case scenario, we need like, I don't know, 1,000 messages, which is nothing. Like I can try to do this on my own. But if we want to train it from scratch, then we need to, like, I don't know, really a lot of examples. By a lot, I mean, like, I don't know, like hundreds of thousands, because neural networks are even worse than regular machine learning algorithms. They need like really much more data. And we actually have a lot of data, but they also need the corresponding output, which is basically the labeling. So this is basically the answer.
Okay. Looking forward to get something touchable, but as I understand, it's not that fast.
Yeah, but yeah, it's not fast, definitely. But as I said, I'm really positive about it. But I look close to this area, and they really. So, for example, this paper about forecasting of
You broke up again.
Again, sorry. Can you hear me now?
Yes.
Yeah, cool. So this paper regarding predicting the Cisco, it was published just like, it was presented at NIPS 2019, which was like, I think 2 months ago or so. So this is super new. Like even for the neural networks area, this is extremely fresh and new. So we can expect like in the next several months, in the next several like, I don't know, in the next year, like a lot of research, and some of it must be meaningful and really of high quality, and then we can see what can be applied. So this area is developing extremely quickly. So just first of all, know about it, like really really know and understand what it is, and keep an eye on it, and like see what the researchers will present in this. Because as I said, I'm really positive about it. Like I think it will be something really great in the future coming about this.
Okay, thank you very much. That was very interesting. Personally, I'll look into some of those things because they seem also very promising. Yeah. If there are no other questions, then we can finish for today. Thank you, Ivan, and thank you everyone else for joining. And have a nice day.
Thank you too.
Thank you.
Bye. Thank you. Bye.
No.
Thank you.
Bye.
Thank you.
Thank you.